All right, last talk of the conference, so thanks for hanging in there. Pretty sure the organizers told me they wanted to save the best for last, so hopefully it'll be worth it to hang in here. So my name is Ken Gibson. I lead a software architecture team at Intel. We are focused on software for NVM with a special focus on persistent memory, the most disruptive version of non-volatile memory. So what I'm going to talk about here is I'm going to talk about what we've been doing with our leading software partners for the last, 3 years, what we've done in the SNEO organization. I'm going to talk about the software architecture we're building out with them. A lot of that will be focused on the native OS level and the native OS APIs. And then I'll talk about the opportunities that creates for software innovation on top of those APIs, especially in the data grid layer. So very happy to be talking to this audience of software developers who are innovating there, in the data grids and the data fabrics. Software developers innovating on in-memory applications, and those who are going to be using, that software on this disruptive new persistent memory technology. So terminology I'll use, I think it aligns with what we've been hearing here for the last couple days. I'll talk about NVM as the general class of non-volatile memory-based, products and technologies, SSDs, DIMMs, NAND, and future stuff. I will mention the NVM Express standard in here at one point, and that's the standard protocol for block access to SSDs over PCIe. And then I'll mostly talk about persistent memory as direct load store memory accessed non-volatile memory, and then the NVDIMMs as the product instantiations that enable that. So this is our view of the problem statement. It's the problem statement that's driving us to persistent memory and this new model of in-place persistence. So the stack on the left is measurements we did by instrumenting one of our NAND-based PCI-attached SSDs. And so that's measuring a 4K byte read from the file system, the standard file read call. And in this stack, it's kind of inverted from how you'd normally think of it. At the bottom is the file read, and then we're measuring the latency as you go through the file system, and then the block I/O subsystem, deliver a command across PCIe, move the data, decode the command in the controller inside the SSD, and then finally at the top is the latency of the media itself. So, of course, for traditional disk drives, that latency would be through the roof. It'd be milliseconds. But you can see here that even with NVM Express, which is quite an efficient protocol, we're at the point here where the latency of the media and everything else to do the I/O is just about equal. So now the middle chart is the same test we did by instrumenting one of our 3D crosspoint-based SSDs. So now on this one, you can see the latency of the media is right there, and everything else is the overhead of going through the file system, the block stack, and over PCIe and everything else. So you can see we're thoroughly overwhelming the latency of the media here as we go to these next generation non-volatile memory technologies like 3D crosspoint. And so, of course, then on the right, we're showing a theoretical chart of the latency for a persistent memory-based access to an NVDIMM based on 3D crosspoint. So this is where we're down to about a microsecond of latency for the media. And in this somewhat idealized picture, we've now eliminated the I/O by moving that right onto the memory bus with memory access. So this is what's driving our motivation to move to true persistent memory. and move to in-place persistence by eliminating the I/O operation altogether. So the Intel hardware engineers looked at this and said, great, problem solved. We've moved to persistent memory. We've gotten rid of the I/O. We've gotten rid of all this overhead. But in my software team, we said, well, wait a minute. There's some problems here. Problem number one is all of the major operating systems today are all designed to assume that memory is volatile. So they don't have the capability to boot up and understand that there might be data retained in memory, to figure out who owns that data, to figure out how to find that data, to figure out how to remap that back into the owning application's virtual address space so you get pointers and data structures and data objects all fixed up again. Operating systems just don't know how to do that. Modern operating systems are all based on the concept that the place where you work on data in DRAM and the media that you persist it on are different, and you have to move data back and forth using I/O operations. So that's problem number one in the software space. And then the programming model that everybody learns in about the first week of their first introductory programming class is how to program to that model. Right after day one, you do the Hello World program. And then in about class 2, you write the program where you allocate a data structure in memory, a string, whatever it is. Then you go open a file, and you do file reads and writes to persist that. That's the dominant programming model. It's so ingrained we don't even think of it as a programming model. It's just the way that applications are developed. And then the third problem is that, traditionally, you do things. Traditionally, in the real world, you do things in that I/O operation, that movement of data between DRAM and the persistent media. So in my picture here, I'm showing, a kernel-based I/O stack with the file system, and I'm showing these things I'm calling optional filter drivers. They might be at the file system intercept layer above the file system at the vNode interface, or they might be down in the block I/O subsystem. But in a real-world operating system, one or more of these are almost always there, doing something, doing security, doing virus scan. They might be doing replication, software RAID. Could be doing a variety of things to layer in important durability and compliance and security functions. So, this is kind of a traditional model for how that's been done. Today, of course, as we're hearing this week, data grids are covering a lot of this. A lot of this is moving up to the user level. But the point is, there's something almost always there in that I/O path as you move the data between your working memory space and where you persist it. So we said, okay, this is a big problem. We at Intel can't solve it by ourselves. We said we need to work with the industry and with our software partners. So what we did is we went to an industry organization that we thought had the right framework and the right partners to go figure out how do we create this new programming model and how do we sketch out the key points of the architecture to support that new programming model. So we went to the Storage and Networking Industry Association, and we created a tech work group, a twig. It's called the NVM Programming Model Twig. We created that in early 2013, I think it was. And then several of our partners quickly jumped in and joined with us. We went to Microsoft, explained what we were doing. They said, oh yeah, we need to be in there with you. VMware, Oracle joined in. Red Hat had never joined SNIA. They had never belonged to SNIA. They joined just so they could join in this twig. HP and several others jumped in, and HP co-led it with us. So we created a critical mass of the right, industry players here to go figure out what's a new software architecture and programming model for in-place persistent memory. We spent about a year, meeting weekly, several face-to-faces, and published version 1.0 of the NVM programming model document. And I think it was January 14 we published that. It's public, and you can go there and download it. But the short summary is it covers 4 aspects of optimizing the software stack for NVM. The 2 on the right in this picture are fairly minor optimizations for block mode access to NVDIMMs, and it's fairly minor but important details of how the BIOS reports the existence and the properties of NVDIMMs, how a device driver detects and attaches. Some fairly straightforward stuff on how we align BIOS vendors and OS vendors and so forth. But then the left 2 get into the really interesting and disruptive part, describing how operating systems, middleware, and applications can use persistent memory for in-place persistence. So that's where it really gets interesting. So this slide is the one-slide view of the programming model covering these four aspects of optimizing for NVDIMMs. So I'm going to spend a few minutes going through this. At the bottom, of course, is the NVDIMM, and like any piece of hardware, at the very bottom of the software stack is a hardware device driver, and that's the NVDIMM driver that I'm showing right here at the bottom. So going left to right here, the first thing we did in SNIA was we acknowledged that this is kind of a new kind of an animal, so there's probably some new aspects of how that has to be managed at the hardware level, probably some new standards that we would want to define. That's a core competency for SNIA. They've done a lot of that. And so we did extend the SNIA common interface model just a little bit to cover these NVDIMMs. But nothing too major disruptive there. And then the middle 2 stacks acknowledge that what you may want to do is you may want to just build a block abstraction on top of this load store access memory. Same idea as the old RAM disk, similar concept. You have a driver that presents it up to the OS I/O subsystem and file system as a fast SSD. And then just like any storage device today, you can either attach your application right to the raw device, or you can access it through the existing traditional file system. So not majorly disruptive there either. So now getting over to the right is where things get interesting. So the spec also defines how a file system can be enhanced to understand persistent memory. And so one of the things it can do, using this path right here, is it no longer has to go through the block I/O subsystem in the operating system. So now the file system itself could just do direct load store access to the DIMM, just use it like memory. So that's slightly disruptive. It is for the file system. But it still keeps it fairly transparent to the application, because you're still using the same file open, close, read, write calls. And more importantly, for the application, you're still keeping this separation of work on your data in DRAM. That's where you operate on it. And then initiate a file I/O operation to move your data to and from persistence. So the application can still use those same POSIX file APIs, and you could still insert, filter drivers in there. They're going to be different kind of filter driver, but you could insert filter drivers, to do those kinds of things that you do in operating systems today. Software RAID, snapshots, a whole range of things. So a little bit more disruptive there. And then that brings us to the final mode on the right. So this is where we've really re-architected some key parts of the operating system and the file system. So again, the goal here is to merge two worlds. The world of memory. You allocate data structures, you have pointers, you use just like in a normal programming language. You allocate variables, you have pointers to it, you use it like memory, right? So we want to merge that world with the world of persisting things and the way file systems, what file systems do, where they keep a directory, an inode structure, on the media so that they can find data, after a restart. They keep that inode structure consistent, so on an unexpected, failure, you're not left with an inconsistent structure for your data. So you're also, when you come back and you need to look up data again, you have the right model for re-authenticating that the application that wants to open a file, that it's got the rights to the file, that the mode that the application wants to use it in is supported by that file. So we didn't want to have to rewrite all that software when most of that is already mature and in place in file systems. So the programming model defines how to extend a file system so that you can use a file system to open a region of memory like a file. So you get that same file APIs, authentication, and so forth for finding your data in memory after a restart. The difference is with a PM-aware file system, it knows that the quote file that you're opening is actually a region of memory. So you go and you do a file open, it returns a file handle that references a region of memory. And so then what an application can do with that is it can go to the traditional mmap or Windows map view of file system call. That's the call that turns a file handle into a memory pointer. The difference is today with an I/O-based device, what the kernel is doing is it's actually caching the contents of that file in memory using the OS buffer cache. We defined what's called DAX for direct access. With DAX, now what the mmap or the map view of file call does is it actually maps those pages of memory right into the application's virtual address space. So that's what this picture is representing here, is that's meant to represent a region of persistent memory in the NVDIMM. And so the application here is, again, it has opened it like a file and then called mmap, so that through mmap, then the OS has then actually mapped that into the virtual address space for the application. Now you're doing memory, right? So now your data structures, your data objects are back in your memory. So that's how you get persistence at that native OS level. So actually, I'll pause here for a second. I think I've got time here. So any questions anybody wants to ask at this point? Because this is a core slide in this, showing this concept of this persistent memory programming model that we've created with our partners. Actually, just a point on status here. So again, as I said, this was published in early 2014. So since then, we, Intel, and others in the Linux kernel developer community, we now have all the enhancements into the upstream kernel. So you can go pull from upstream, and you can build Linux with ext4 with this supported. I can't speak to specific schedules for distros, but we are expecting to see major distributions coming out later this year with DAX and PM-enabled ext4. So we expect those towards the end of the year. And then on the Windows side, Neil Christensen, who's one of the senior architects in the Windows team, he has publicly presented their architecture in Windows to implement this programming model. Didn't make any commitments on schedule, but he did clearly show, they have thought through their architecture, they have their architecture in place, and they're now publicly presenting this. So I could take a minute for a question or two if anybody's got a burning question on this. Yeah, go ahead.
It's, where's the TLB? Where's the IO review? How does that work?
The TLB?
Yeah, in this picture.
The TLB, it's in the memory controller in the CPU. So you have, when the mmap call in the kernel, it set up the TLB tables to map that physical memory into the application's virtual address space. So that, that OS mmap is where that TLB mapping happened.
No change there. It's the same way you use it with the existing RAM.
Yeah, that's right. That's right. The NVDIMM is on the DDR bus, so at that point, the memory controller in the CPU and the TLBs can all get set up just like a DIMM today. Yeah, actually, there was a question here.
Yeah, so you are actually, as you said, you open a segment of the address space.
Right.
So, but like all this can actually be shared across multiple programs? Because if yes, then it has to be mapped to different parts of the address space for different programs.
Right. So initially, the DIMM is just a piece of physical memory. So using the file system model, when an application wants to open a region of that, that's step one in ensuring security, that the application has the rights to open that region of memory, exactly like the way you open a file on an SSD today. And then it's the mmap that's actually mapping it into the protected memory space of the application. So you've got both of those mechanisms get reused for how you maintain your protections around that region, around that data. So yeah, let me take this question, and then I'll continue on so I don't go totally over time here.
Yeah, I'm not sure if my question makes really sense, but I ask anyway. When we say file API and file handles, what about object?
So we are focused today on the step of getting the native OSs, operating systems, with their native standard file interfaces interfaces supported. So the question is how are objects used, right? So you might build an object abstraction on top of files, right? Might be one way that you do that. So I think that might be a common way. But tell you what, in 2 more slides, I might answer your question. Yeah, okay, last one.
Data protection. The data clouds, how do you cope with the data protection, the data protection, like ECC or some sort of...
So ECC, that's going to depend on the specific NVDIMM product instantiation, but we would envision that, NVDIMMs are going to have, ECC built in. Also, Intel completely understands the importance of, data at rest security. And so because, when we build one of these, because it persists data, we're going to have the right keys built in here so that we support, data at rest security and the ability to do, secure erase. And yeah, the data will be, scrambled down on this device. So all right, I'm going to continue on, but then I can stay. We're the last talk of the day, so I can stay longer to answer questions. So okay, so now you've got an application that can do something that it could never do before. It can interact directly with the persistent media. Today, there's all kinds of layers in between the application and the actual persistent media that's down inside the SSD. So great, our application's ready for that, and I think in many cases the answer is no. So to help applications at the native API level, we started an open source project. It's called. We have 2 names for it. We call it the NVM libraries, NVML, but publicly we mostly call it the PMEM libraries. And fully open source, It's all happening right here. So, there's the web page and the link to the GitHub. And so what this is, it's a set of helper functions to help applications, use this new tier of memory either as a high-capacity volatile memory, or as persistent memory. So, you could, so like I just described, we'll have PM-enabled file systems that can manage, the layout of objects and regions on the DIMM. So you could, every time you allocated a data structure, a variable in persistent memory, or a data object, you could go to the file system, right? You could go back into the kernel and file system, and you could create little files for every data structure. But that's going to be pretty inefficient. One of the key ideas of the programming model is once you've opened the file through the file system and then gone to the kernel to mmap it, the kernel's out of the way. The file system's out of the way. It's just your direct memory. So you don't want to have to keep going back into the kernel all the time. What you want to be able to do, probably in most cases, is open a big region of persistent memory, and then you want something like the traditional standard libraries for malloc and free to be able to allocate data structures, data objects in there, just like you do off the DRAM heap today. So that's one of the things this set of libraries does, is you've got the vmem and vmalloc, and they're actually heavily leveraged existing open source memory management APIs, but they're modified to handle multiple regions that you may want to open on an NVDIMM. So we have libraries to help there, and I skipped over one here called libpmem. So this point's come up a couple times, at least a couple times here in the conference, is so you write a C++ program, it allocates a variable, you have a pointer to it, you dereference the pointer and write a value into that variable. That doesn't mean that data is all the way out on the persistent media and it's persisted. It may have gotten cached in the internal, caches in the CPU. It could still be maybe in a controller on the DIMM. So you want to have a way that, when you've got a data structure already, all consistent, be it a data object representing a transaction, whatever, you want to make sure that it's persisted. So libpmem includes a set of functions to abstract that for the application. So it'll abstract whatever mechanism you need in the hardware to either push the data out, at that time, or to make sure that on a power failure it gets pushed out. Libpmem abstracts that all away and just gives you a simple set of functions to say, for a program to say, okay, I want to commit a transaction. It's called pmem persist is the call, and it'll make sure that it's persisted on that DIMM. It's either now or on a power fail. It's going to get all the way out onto the persistent media. So then we have a set of functions for persistent use, and these give you atomic and transactional updates into your persistent memory. Again, something that file systems in the I/O subsystem typically handle for applications. So most applications don't worry about it, except for those of you doing in-memory data grids. But the idea is, the typical example is you're inserting an element into a doubly linked list, and you get halfway through updating pointers, and you have an unexpected failure. So you come up, and now you've got a persisted, corrupted doubly linked list. And so what these libraries do is they give you a simple way to maintain an undo log, and then to ensure on a power failure that complete transaction either completes or gets rolled back on a restart. So just basic functionality there that applications are going to want to have as they start interacting directly with that persistent media. So again, open source project where we want collaborators and contributors here, and mostly we need software innovators building on top of this. we view this as just the baby step to getting started with using persistent memory. And so just a quick word on status on this. This is now lined up to go into, I think it's in OpenSUSE now, I think it's in Fedora now. We're pretty well lined up for this to come into RHEL as they release their version that supports DACs. And Microsoft has publicly stated that they intend to bundle NVML as their common API for persistent memory use in Windows. So we got good start and good momentum as the initial base native OS API for persistent memory. So okay, so you have persistence. So what? I think, Amit, I liked your comment earlier that this was a sensitive topic, right? Not sure it's so sensitive. It's just something that we need to be aware of. So persistence, right? So you can put your data in a DIMM, and it's retained through a power failure. Okay, great. But what you really want is durability, which I define as you don't lose your data on a failure, and you also don't lose access to your data on any failures. So that's basic durability. And then for so much data that gets stored on servers, it also has to be compliant. So if you're storing financial data for a publicly traded company, if you're storing data for a bank, if you're storing all kinds of data that companies store that have legal requirements around archiving and authenticating, and there's compliance requirements sometimes that say you have to do snapshotting every regular period of time, what used to be called CDP, continuous data protection. So all that stuff for decades, all that has been accomplished by inserting functionality in that I/O operation, in that move between your working memory and where it's persisted. So if we're going to do in-place persistence, now what do, right? We don't have that move. We don't have that move anymore, right? So this is where we need your help. Again, I'm showing that the traditional OS-based filter drivers here. 15, 20 years ago, that was a common place to do these things. Over time, I think a lot of it moved out to the EMC and the NetApp arrays and others. I actually think now it's moving up to the data grid and data fabric layer, and that's a good thing. That's a good thing for our goals to enable large persistent memory in the server platform. So one idea that we're experimenting with in the pmem.io open source project is, so like I showed earlier, you can use an NVDIMM by just plugging it in and putting a block driver abstraction underneath it, right? Keep your I/O operation, even though you actually may just be copying the data directly using memory load store. So full DACs, again, that's in-place persistence. We got the challenge. How do you insert this stuff in there? So one idea we're playing with is, as we move up to user mode, just like the data grids and data fabrics, hey, let's emulate the file interfaces, and let's just fake out an application so we're dynamically linking to a user mode library that brings back the simulated I/O here, even though it's all within the user space of the application, within its protected memory. So, one half step that we want to experiment with, in the open source through our NVML project. But what we really want to get to is, how do we do this stuff for in-place persistence? So the one hook point we do have is, as I described earlier, just because you do writes to a data structure or a data object in memory, that doesn't mean it's persisted. So we do have the concept of the persist point. When your data object's all ready, it's consistent, or your transaction's completed, an application, we want to condition application developers that then you call persist. or some variation of that. So that gives you a hook point there where you can say, all right, now we can plug in functionality there, such as RDMA to another server in another rack in the data center to give you durability, right? And so where we're looking for the thinking from smart people is, okay, now how do you do that for the other kinds of compliance functions? Can you, for example, say, okay, the application says it wants to persist this data. Okay, we know it did something significant like complete a transaction. So that might be a good time to say, all right, let's take a snapshot of the memory, and then as a background task, let's replicate that snapshot back to, cheaper block storage or backing object storage, right? And all the other things that you want to do in the real world, right? And I'm showing in the picture here, I'm showing that as a plug-in to NVM library, whether it's a plug-in or it runs on top or underneath, don't know yet. We'll figure that out through the open source process. So I think this slide was used earlier. It's our slide. I was happy to see someone else using it. So what this helps us together build to is this future where now terabytes of persistent memory become the new in-place working storage tier. So we move from today, where you do this tiering. Again, DRAM is just where you operate on your data, but you quickly get it persisted to some expensive, high-performance, I/O-based tier. And then, of course, eventually it migrates back to object storage like Amazon S3 or whatever or Ceph or whatever your favorite high-capacity tier is. So the future is, instead of trying to differentiate between how fast the I/O takes here versus the I/O here, the question is, for which persistence mechanisms can you tolerate the overhead of that I/O operation that I showed back at the beginning? That becomes the key dividing line between what goes in your top tier and then what goes down into your higher capacity but lower performance and lower cost tiers. So that's the future end state, and that's the opportunity for software innovation. Is how together do we build this? Intel's building the 3D XPoint. We need the developer community developing the software that makes this real. So a couple links on how to join in the open source project, how to join in the discussion. So again, the programming model document, that's the Open Industry Programming Model, published by SNIA. Our NVML open source project, pmem.io. And then various lower level details for those interested in getting down closer to the server hardware and what we're doing there to standardize interfaces at the BIOS level and so forth. So thank you. So I'll finish with that picture. So questions? Yeah.
Can you describe the linkage between the pmem persist system call and the pcommit, assuming that pmem persist flushes things like you said? So does it turn into one or more pcommits or does the pcommit flush everything out of the persistent?
So pcommit would flush everything. So we haven't, just to be clear, we haven't committed that pcommit's going to be the instruction. We've publicly disclosed that as we've reserved that as a new instruction in the Intel instruction architecture that we may be using. But in the case of a platform that has pcommit, NVML, pmem persist would just turn right into a pcommit instruction. And that's a non-privileged instruction. Applications can call it. So, it's just a straight call to a machine instruction. So that does retain, some of the beauty of this programming model is instead of having to call into the kernel, go into a file system, give the OS the opportunity to decide that maybe it needs to reschedule, maybe it needs to put your application to sleep for a while. So instead of having all that potential, variation in your latency, you're just calling right into, machine instruction. Or what PERSIST will do is it will have figured out that you're on a platform that can flush data on a power fail, and then it just becomes a no-op. So that's the ideal scenario. Is it's a no-op, and bam, you're continuing on running again.
So follow up to that, I guess PERSIST can happen on bigger structures than a cache type, or is it?
Yes.
So then it would turn into one or more p-commits based on what you're trying to flush? P-commit, I thought, I heard earlier today, it's a cache line based thing.
It's, no, it'll flush multiple cache lines. It'll flush the cache lines that are dirty. But, the granularity of within that is, the idea is it is cache lines that are getting flushed out. So that's one mechanism, or there's other mechanisms as well that we have for, getting a cache line, pushed out to the DIMM.
Typically, if it's in an on-time cache, it's like a version or a copy of it sitting in DRAM. So the p-commit will flush it really all the way to persistent bits out of the DRAM.
Yeah, or in this model, there's no DRAM in the path, right? It would be, it would be in the processor cache pipeline still, and it just push it out, so you're good on a power failure.
So then the way the loader store works, you can read directly from the non-volatile into the processor cache.
Yep, that's right.
Okay.
Just like memory reads and writes today. Yes, that's right. That's right. Yeah, that's right. Yeah, I think we've announced that we have announced that Perl is the first platform that will have the ability to support DIMMs, but we've not made any commitments on when DIMMs will come out. So, but you're right. Yeah, and also the application may want to be aware as well. So in this programming model, an application can see a mix of DRAM and NVDIMMs, and so it can make decisions about which data goes in which. Yes.
Is this applicable for the memory with no volatile memory with light endurance, limited light endurance?
So the question was around the endurance of this media. And so this media, the 3D crosspoint media, will not be like NAND. It has a wear life that is several orders of magnitude, greater than NAND and much closer to DRAM. And so, when Intel builds NVDIMM products based on 3D crosspoint, I mean, we'll be designing those so that they will have the wear life and the endurance of DRAM. So you can use them just like memory.
Do you have like mirrored DIMM sets as well in offering for high availability or redundancy?
The question was around mirrored DIMM sets, and I assume you mean mirroring within the platform. Yeah. So yes, that's I can't commit on specific product plans, but as you probably know, I mean, Intel supports mirrored DIMMs on many of our platforms today, and so that's a feature that I would expect that we'd be planning to support for these as well, and as well as as I described here for durability, we're going to be defining reference architectures for very efficient RDMA across servers as well. And that's of course the other nice benefit of NVDIMMs is they are memory, so you can RDMA to and from them without having to do intermediate steps, through memory and then do block I/O like you do for an SSD today. So we envision that, so again, and along the theme of, hooking into the PERSIST, that's one of the initial, uses we expect that we'll want to build in the software stack, because a PERSIST both flushes locally and does an RDMA, through something like an RDMA verbs mechanism to a pre-allocated, mirror copy of that memory. So that's one of the ways we envision achieving durability.
Are you thinking maybe even memory blades that might be a store cache for?
Yeah, I mean, possibly. I mean, I don't think we've thought through all those specific configurations yet. That's a great question. So in that programming, the question was, do you still need I/O-based storage? And that's a great question. So in that programming model diagram that I showed, I mean, you could imagine taking your NVDIMMs or an NVDIMM and using some of it to create a block abstraction on top of, and then others as direct, persistent memory. So yeah, you still want a block SSD to boot from, or for some reason, some uses, you could do that. So. I know what I would do. Yeah, so you had a.
I was just wondering, with this new architecture and this new design, any thoughts on what problems it might create?
Well, I think the big one is, what I described here is how do you layer on, durability and compliance so that you can truly use this as a, trusted storage. I mean, coming from the software and solution perspective, I mean, that's the big problem. But therein lies the opportunity as well. And so I love some of what I've heard here about the functionality of the data grids and data fabrics, already working on that problem of take in-memory data and make it durable.
Do you envision how, like, monitoring or application performance tools would interface with this? Seems like you're bypassing a lot of the operating system mechanisms.
Yeah, I think, you want new tools for instrumenting your application. Intel develops some. We have a tool called vTune that helps with that. Helps you as an application developer figure out what your memory access pattern look like. And so yeah, good point. That's another opportunity. Is how do you help applications figure out which of their data might want to stay in DRAM and what can tolerate latencies that are more than 100 nanoseconds. Okay, well, thanks, everyone. I think we're at the end of the conference. Thank you.